Today we'll be exploring one of the most essential systems in the human body, the digestive system. We'll look into how the organs of the digestive system from the mouth to the intestines process food step by step. Then we'll connect it to nutrition, learning about how carbohydrates, fats, proteins, and vitamins, as well as minerals, fit into the big picture of maintaining health and energy balance. When we think about food, we usually focus on taste, but biologically, food is fuel and raw materials. Before our cells can use it, the body must process it through the process of digestion. This involves several key steps: intake of food, mechanical breakdown, chemical digestion, absorption of nutrients, and elimination of waste. Every meal you eat undergoes this journey. The digestive system's job is to transform complex foods into molecules small enough for cells to absorb and use. The digestive system is essentially a long muscular tube called the gastrointestinal or GI tract. Inside is the lumen, the hollow space where food passes through. Even though food is inside your body, it truly isn't in your body until it's absorbed through the tract's wall. The GI tract includes the mouth, the pharynx, the esophagus, stomach, small intestine, large intestine, rectum, and anus. Surrounding it are the accessory organs, the salivary glands, liver, gallbladder, and pancreas, which release enzymes and secretions that make digestion possible. If we take a cross-section of the GI tract, we'll see four main layers working together. The mucosa lines the inside and directly touches food. It secretes mucus and enzymes. The submucosa lies underneath and contains blood vessels, lymphatic vessels, and nerves. The muscularis provides smooth muscle contractions that move food, and the serosa is the outermost protective layer. Between organs are the sphincters, which these are thick rings of muscles that act like valves, opening and closing to control the movement along the tract. Every organ in the digestive system contributes to 5 key processes. First is mechanical processing, like chewing and churning, which physically breaks down food into smaller pieces. Next is secretion, which releases fluids, enzymes, acids, and mucus. Then comes digestion, the chemical breakdown of large molecules into their absorbable forms. Absorption follows, and that's where nutrients and water pass through the intestine lining into the blood or lymph vessels. Finally, elimination removes what's left over as feces. Each step depends on the last, forming one continuous digestive flow. Movement within the GI tract happens through smooth muscle contractions. The first kind is known as peristalsis. That pushes food forward in a wave-like motion. The second, segmentation, mixes food back and forth, blending it with digestive secretions. Together they ensure food moves efficiently but also spends enough time mixing so the enzymes can work and absorption can occur. Without these rhythmic contractions, digestion would come to a halt. Digestion begins in the mouth, where teeth and the tongue team up to prepare food for swallowing. Teeth come in different shapes and sizes. Incisors are used to cut, canines are used to tear, and molars are used to grind food into smaller pieces. Adults have 32 permanent teeth, while children roughly have 20. The tongue, made up of skeletal muscle, helps move food around, forms it into what is known as the bolus, and pushes it to the back of your mouth for swallowing. It's also covered in taste receptors that trigger salivation and help start digestion. Saliva is the first digestive fluid we produce. It comes from the parotid, submandibular, and sublingual glands. Saliva's ingredients have special jobs. Mucin lubricates the food, salivary amylase begins starch digestion, bicarbonate keeps the pH ideal for enzyme activity, and lysozyme also helps prevent bacterial growth. This means that digestion and protection both start right in your mouth. Swallowing starts voluntarily when the tongue pushes the bolus into the pharynx, but once it hits that point, it becomes an involuntary reflex. The epiglottis closes off the airway and food doesn't enter the trachea. The esophagus takes over after this, using peristaltic waves to move the bolus down towards the stomach. At the end of this tube is the lower esophageal sphincter, which opens up to let food into the stomach and then closes to prevent acid reflux. The stomach is a muscular storage chamber that temporarily holds food and begins chemical digestion. especially of proteins. It mixes food with gastric juices to secrete and create a semi liquid mixture called chyme. The stomach is also carefully regulates when and how much chyme moves into the small intestines using the pyloric sphincter. This ensures digestion happens at a steady, controlled pace instead of overwhelming the intestines. Inside the stomach, specialized cells produce gastric juice, which is a mixture of hydrochloric acid, intrinsic factor, mucus, and pepsinogen. The acid creates a pH of about roughly 2, breaking large food particles apart and activating pepsin from pepsinogen. The pepsin starts digesting proteins into smaller fragments. The intrinsic factor is essential for absorbing vitamins B12 later in the small intestines. Meanwhile, mucus protects the stomach lining from being digested by its own acid, preventing ulcers and injury. Now, you might wonder, with all that acid, why doesn't the stomach just digest itself? The answer lies in the protective mucus barrier. This thick coating of mucus lines the stomach wall and prevents the acid and enzymes from damaging the tissues beneath. But when this barrier breaks down due to infections, chronic stress, or long-term use of anti-inflammatory drugs, an ulcer can actually form. A peptic ulcer is essentially an open sore in the stomach lining and is often linked to Helicobacter pylori, or H. pylori, which is a bacterium that can survive in acidic environments. The stomach is just not a storage pouch. It's an active mixer. Rhythmic contractions in the muscular walls churn food, blending it with gastric juices to create chyme, which is a smooth, semi-liquid mixture. Peristaltic waves push chyme towards the pyloric sphincter, releasing small amounts into the small intestines at a time. This careful control ensures that the intestines isn't overwhelmed. It takes about 2 to 6 hours for the stomach to empty completely after a meal. The stomach doesn't absorb nutrients, but a few substances like aspirin and alcohol can pass directly through its lining. When chyme enters the small intestine, it meets a new set of chemical helpers, enzymes and bile, that contribute and continue digestion. The small intestines neutralize the stomach acid, breaks down proteins, carbohydrates, and fats, and absorbs about 90% of all nutrients and water. This section is the true workhorse of the digestive system. Most of the breakdown and absorption happens here, making it vital for maintaining energy balance and overall health. The small intestines is divided into 3 regions. The duodenum is the first section where most digestion occurs as enzymes and bile enter. The jejunum and ileum focus on nutrient absorption. Its internal surface is highly specialized for absorption. It has large circular folds, finger-like projections called villi, and even smaller microvilli on the epithelial cells. This microscopic design dramatically increases the surface area, ensuring that nutrients have maximum contact with all of the absorptive cells. Now let's bring in the accessory organs, the salivary glands, pancreas, liver, and gallbladder. These organs never touch the food directly, but are absolutely critical to digestion. They produce enzymes like bile and other substances that help break down food into absorbable components. Think of them like the chemical support team that makes digestion efficient and precise. The pancreas plays a dual role, but in digestion it acts like an exocrine gland that releases enzymes and sodium bicarbonate into the small intestines. Bicarbonate helps neutralize stomach acids so the intestinal enzymes can work properly. The pancreatic enzymes themselves are powerful. Protease like trypsin and chymotrypsin digest proteins. Pancreatic amylase breaks down starch. Lipase digests fats. Without the pancreas, nutrient absorption would be nearly impossible. The liver is the largest internal organ and serves as a biochemical factory. It produces bile, which is a fluid that emulsifies fat, breaks large fat droplets into smaller ones so enzymes can digest them more easily. The liver also produces and stores nutrients absorbed in the intestines. Though the hepatic portal system, nutrient-rich blood from the digestive tract flows directly to the liver for filtering, storage, and detoxifying before entering general circulation. The liver does more than digestion. It stores fat-soluble vitamins like A, D, E, and K, as well as glucose in the form of glycogen, releasing when the blood sugar drops. It synthesizes plasma proteins like albumin and fibrinogen, which make certain lipids, and detoxifies harmful substances, everything from alcohol and drugs to ammonia, which it converts into urea for safe excretion. It even recycles components from old red blood cells. In short, the liver is a central hub for metabolism and homeostasis. After the small intestine finishes its work, what remains enters the large intestines. Its main job is to absorb remaining water and electrolytes, forming solid feces. It also serves as the temporary storage before elimination. The large intestines include the cecum, the appendix, and the colon, including the ascending, transverse, and descending colon, as well as the sigmoid sections, and the rectum and the anus. Although little digestion happens here, this region is key for water balance and waste removal. The large intestines is also home to trillions of microorganisms collectively called the intestinal microbiota. These microbes aren't just harmless passengers, they're essential partners in our biology. They produce vitamin K, which break down dietary fibers into beneficial short-chain fatty acids, and may even lower the risk of disease like type 2 diabetes and colon cancer. A healthy microbiota is also protects us from outcompeting harmful bacteria for space and nutrients, keeping our gut environment balanced. Now that you've seen how food moves through the GI tract, let's talk about what actually happens to the macromolecules inside, starting with proteins. Proteins are digested by the team of enzymes from the stomach, pancreas, and small intestines. In the stomach, pepsin begins breaking proteins into smaller chains. Then pancreatic enzymes like trypsin, chymotrypsin, and carboxypeptidase continues the process in the small intestines. The intestinal enzymes finish the job producing amino acids, which are absorbed by the active transport through the intestinal cells and then enter the bloodstream. Carbohydrates begin digestion in the mouth with salivary amylase, but the heavy lifting happens in the small intestines. Pancreatic amylase breaks starch into smaller sugars, and enzymes in the intestinal linings complete the conversion to monosaccharides like glucose. These simple sugars cross the intestinal cells by active transport and move into the bloodstream for facilitated diffusion. Once absorbed, they are carried to the liver, which regulates how much glucose stays in circulation. Lipids or fats are handled differently because they're not water soluble. In the small intestines, bile from the liver emulsifies fat, breaking them into smaller droplets. Then lipase from the pancreas and intestinal cells break them down into monoglycerides and fatty acids. Inside the intestinal cells, these components are reassembled into triglycerides and packaged into chylomicrons, which are lipid protein complexes that can travel through the lymphatic system before eventually entering the bloodstream near the heart. Besides the macronutrients, the small intestines also absorb water, vitamins, and minerals. Water moves mainly by osmosis, following solutes. Fat-soluble vitamins like A, D, E, and K dissolve in micelles and are absorbed along with lipids, while water-soluble vitamins use active or facilitated transport. Minerals such as calcium, sodium, and iron are actively transported or absorbed by diffusion, depending on the body's needs. Digestion just doesn't happen automatically. It's tightly coordinated by the nervous system and hormones. Stretch receptors in the stomach detect how full it is and send reflexes signals to increase peristalsis and gastric secretions. Meanwhile, hormones like gastrin, secretin, and cholecystokinin help fine-tune each stage of the digestive system. They regulate enzyme release, bowel flow, and how fast food moves from one organ to another. Let's take a closer look at those key hormones. Gastrin is released when the stomach stretches or senses proteins. It triggers the release of gastric juice. Secretin is released from the duodenum when acidic chyme arrives. It tells the pancreas to release water and bicarbonate to neutralize the acid. CCK, or cholecystokinin, also from the duodenum, responds to fats and proteins. It signals the pancreas to release digestive enzymes and tells the gallbladder to release bile. Together, they ensure digestion runs smoothly from stomach to the intestines. General recommendations for food nutrition are pretty straightforward, but often ignored. Eat a variety of foods, maintain a healthy weight, and include plenty of fruits, vegetables, and whole grains. Sugar and salt should be limited, as should alcohol. The key idea is balance. A healthy diet supports every system of the body, from the nervous system to the immune system. Carbohydrates are our body's preferred fuel source, providing about 45 to 65% of daily calories. Simple carbohydrates like sugars gives quick bursts of energy, but complex carbs, which are found in whole grains, fruits, and vegetables, are digested more slowly, providing sustained energy and fiber. Whole foods are always better than processed ones because they include fibers, vitamins, and minerals that simple sugars lack. Fibers also support gut health and control blood sugar levels. Lipids or fats are essential but must be consumed wisely. Saturated fats found in meats and dairies can raise LDL cholesterol levels, while unsaturated fats from plant oils and fish tend to lower LDLs and reduce heart disease risk. Trans fats, on the other hand, are worst offenders. They're artificially hydrogenated oils that increase bad cholesterol. Fat should be about 20 to 35% of your calories, focusing on unsaturated sources like olive oils, nuts, and fish. Let's go a bit deeper into the fats. Two essential fatty acids, linoleic acid and linolenic acid, must come from food because our bodies can't make them. They're vital for healthy cells, membranes, and hormone production. Even though fats are necessary, most people consume too much. The key is moderation. Lipids should make up no more than 20 to 35% of daily calories, and we should limit saturated fats, trans fats, and cholesterol, since these are linked to heart disease and some cancers. Aim for balance. Healthy fats like those from fish, nuts, and olive oil support brain and cardiovascular health. Proteins are made up of amino acids, the building blocks of life. Out of the 20 amino acids, 9 are essential, meaning we must obtain them from food. A complete protein contains all 9 essential amino acids in sufficient amounts. These are typically found in animal sources like eggs, meats, and dairy, also found in soy. Most plant proteins are incomplete, missing one or more essential amino acid. This is why vegetarians often combine foods like beans and rice to form a complete amino acid profile. Now let's talk about vitamins, those small but mighty organic molecules that keep everything running smoothly. We need at least 12 different vitamins, which fall into 2 major categories: fat-soluble and water-soluble. Fat-soluble vitamins like A, D, E, and K are stored in the body fat and don't need to be eaten daily. Water-soluble ones like vitamin C and B complex are not stored long-term, so they must be consumed regularly. Vitamins act like coenzymes, helping enzymes speed up chemical reactions that support metabolism, growth, and repair. Minerals are the inorganic counterparts to vitamins. They're simple elements that play critical roles throughout the body. Some act as ions that maintain electrical balances in our cells, like sodium and potassium and chloride. Others are structural, like calcium and phosphorus, which strengthen bones and teeth. Minerals also regulate nerve and muscle activity, and some, like iron, form parts of the large molecules like hemoglobin. The recommended dietary allowance tells us how much of each vitamin and mineral we should aim for daily use to stay healthy. We classify minerals based on how much the body needs. Major minerals such as calcium, potassium, sodium, magnesium, and phosphorus are required in amounts over 100 milligrams per day. Trace minerals like iron, zinc, iodine, and selenium are needed only in tiny amounts, but are just as essential. For example, iodine is crucial for thyroid hormone, while zinc supports immune functions and wound healing. Even though they're trace, deficiencies can actually have major side effects. Now let's talk about fiber, the unsung hero of nutrition. Fiber comes from undigestible plant material found in fruits, vegetables, and whole grains. It adds bulk to stool, helping it move smoothly through the intestines. Low fiber diets can lead to constipation, hemorrhoids, and diverticulosis, and they're linked to higher risks of colon cancer. A high fiber diet, on the other hand, supports a healthy gut microbiome and helps regulate cholesterol and blood sugar levels. Fiber doesn't give energy, but it's essential for digestive health. Everything we've eaten so far provides energy, but how much we do actually need? That depends on our basal metabolic rate, our BMR, the amount of energy your body uses at rest for essential activities like breathing, circulation, and temperature regulation. Your BMR is influenced by age, gender, and body composition. As we age, BMR decreases, meaning we need fewer calories. Most people burn about 50 to 100% more calories than their BMR through daily activity, so balancing food intake while energy use keeps weight stable. To maintain a healthy weight, calories in must equal calories out. Consuming more than you burn leads to fat storage and weight gain, while eating less than you results in weight loss. Every 3,500 calories burned equals about 1 pound of fat lost. Fat cells shrink when we lose weight, but never completely disappear, which explains why weight loss can be difficult to maintain. Consistent physical activity is key for long-term balance and metabolic health. Maintaining a healthy body weight is one of the most powerful ways to prevent disease. Obesity increases the risk of heart disease, diabetes, arthritis, and certain cancers. We measure weight status using our BMI, our body mass index. A BMI between 18.5 and 25 is considered healthy. 25 to 30 is overweight, and over 30 is obese. Keep in mind, BMI is a general tool, and it can overestimate body fat in very muscular people or underestimate those in low muscle mass. At the other extremes are eating disorders, which involve dangerous patterns of eating and emotional distress. The most common are anorexia nervosa, bulimia nervosa, and binge eating disorders. Anorexia involves severe food restrictions and can lead to starvation. Bulimia combines binge eating and purging through vomiting or laxatives. Binge eating disorders involve uncontrolled overeating without purging. These conditions are most common in young women and often found they stem from psychological, social, or cultural pressures. They're medical and mental health issues that require compassionate, multidisciplinary care. Sometimes digestion goes wrong because of what is in our foods. Food poisoning happens when we eat foods contaminated with bacterial toxins. These toxins can cause nausea, vomiting, and diarrhea, and in serious cases, even paralysis. That's with Clostridium botulinum, the bacterium that causes botulism. Foodborne infections, on the other hand, come from swallowing living microorganisms like E. coli, salmonella, or norovirus. These symptoms are similar: abdominal cramps, diarrhea, dehydration, but caused by infections rather than toxins. Hydration is crucial because fluid loss can be dangerous. Another food issue is food allergies, which occurs when the immune system mistakenly reacts to harmful food proteins. The body releases histamine, causing symptoms like hives, swelling, vomiting, or even diarrhea. In severe cases, it can actually lead to anaphylaxis, which is a life-threatening allergic reaction. Common allergies include peanuts, shellfish, milk, and eggs. The best management is a complete avoidance that triggers food. For mild reactions, antihistamines can help, but for severe cases, epinephrine is needed immediately. Unlike allergies, lactose intolerant isn't an immune response. It's a digestive enzyme issue. Most infants produce the enzyme lactase to digest lactose, the sugar in milk. As we age, many people lose the ability, especially in certain ethnic populations. When lactose isn't digested, it ferments in the large intestines, producing gas, bloating, and cramps. The solution is simple: avoid dairy, choose lactose-free products, or take lactase supplements when consuming milk. Peptic ulcers are open sores that develop in the lining of the stomach or upper small intestines. Most are caused by infections like Helicobacter pylori, a bacterium that thrives in acidic conditions. Ulcers can result from long-term use of pain relievers like aspirin or ibuprofen, which erode the protective mucus layer of the stomach. Treatments include antibiotics to clear H. pylori and antacids, or proton pump inhibitors to reduce acid and allow healing. Now let's talk about gluten, a protein found in wheat, barley, and rye. Some people can't tolerate it, and that intolerance can appear in a few different forms. There's celiac disease, which is an autoimmune disease, wheat allergy, which is an immune-mediated and non-celiated gluten sensitivity, which is less well understood. Although the symptoms can overlap, abdominal pain, diarrhea, and fatigue are the underlying causes are more different, which is why accurate diagnosis is very important. In celiac disease, the immune system attacks the lining of the small intestine after gluten is consumed. This damages the villi, which are crucial for nutrient absorption. Over time, that leads to malnutrition, fatigue, and weight loss. Even in someone who is eating enough food, diagnosis is done through blood tests and detects antibodies specific to celiac disease. The only effective treatment is a strict gluten-free diet, which allows the intestinal lining to heal and prevent long-term complications. A wheat allergy is different. It's classical allergic reactions mediated by IgE antibodies. Symptoms appear quickly after eating wheat and may include hives, swelling, and respiratory issues, or even asthma-like reactions. Diagnosis involves a skin prick test or a blood test for IgE antibodies. Management focuses on strict avoidance of wheat and having emergency medications such as an epinephrine autoinjector in severe reactions. The most common but least understood form of gluten intolerance is non-celiac gluten sensitivity. People experience symptoms like gas, bloating, fatigue, headaches, even skin rashes after eating gluten, but the test is negative for both celiac disease and wheat allergy. A gluten challenge test is used for diagnosis where gluten is removed and then reintroduced to see if symptoms return. Interestingly, recent research suggests that symptoms might not come from gluten itself, but from certain carbohydrates and wheats that are hard to digest. Colon polyps are small, usually harmless growths that develop on the inner walls of the large intestine. While most are benign, some can become cancerous over time. This is why colonoscopy screenings are so important. They allow doctors to detect and remove polyps early. Removing them significantly reduces the risk of colon cancer, which often starts silently and develops from these small growths. Finally, let's look at the disorders that affect the accessory organs, particularly the liver. Hepatitis means inflammation of the liver and most commonly caused by a viral infection. Hepatitis A is spread through contaminated food or water and usually causes mild illness. A vaccine is available and highly effective. Hepatitis B, however, spreads through blood and body fluids, such as during unprotected sex or needle sharing. They can cause chronic infections leading to liver failure or even cancer. Fortunately, it's also preventable with vaccines. The last of the major hepatic viruses is hepatitis C, which is transmitted through infections in the blood, most often from contaminated needles, blood transfusions before 1992, or organ transplant before screening became routine. What makes hepatitis C tricky is that it can remain asymptomatic for years, silently damaging the liver until it leads to cirrhosis or liver cancer. Fortunately, modern antiviral medications can now cure most cases completely. Anyone who receives a transfusion before the early 1990s should get tested. The gallbladder is another accessory organ prone to problems. Its main job is to store and concentrate bile, but sometimes cholesterol, bile salts, and calcium crystallizes to form gallstones. Small stones might pass unnoticed, but larger ones can block bile duct, causing sharp pain after meals, especially those in high fats. Treatments include medications to dissolve the stones, ultrasounds or laser therapy to break them apart, or surgical removal of the gallbladder. The liver continues to make bile afterwards, so digestion remains functional.